Hello, everyone, and welcome back to the Blue Waters webinar series. My name is Maxim Belkin, and today I'm joined by my colleague Scott Lathrop, and we are glad you found time to join us today, as this is the first webinar in our fall of 2019 webinar session, and we are excited to continue this series. Before we begin the webinar, I'd like to say a few words about upcoming webinars. So currently we have 4 webinars scheduled in this session with only 1 week between them. 3 of the scheduled webinars fell under the scientific software ecosystems track, but all of them are on very different topics. So if you are watching a recording, consider registering for this track. You will learn about very different and interesting tools. The next interesting item is that 2 of the webinars, of the scheduled webinars, will be presented by NVIDIA staff, which is, I find it quite interesting. Finally, we might have 1 additional webinar at the end of these sessions, so stay tuned for that. And today, I'm pleased to welcome Scott McMillan. Scott is a senior solutions architect at NVIDIA, and where he works on applications related to high-performance computing. Interestingly enough, though not surprisingly, Scott has a PhD in chemical engineering from Northwestern University, where I did my first postdoc. Today, he will talk about his software solution called HPC Container Maker, which allegedly makes software containers easier to work with. You can find more information about Scott and today's webinar on the webinar page on our portal. As always, I'd like to remind everyone that you can ask questions on YouTube and in our Slack channel. Information on how to join our Slack team can be found in the sidebar below. With that, I'd like to thank Scott for joining us, and take it away.
Okay, thank you. Thank you for the opportunity to be here today. Yeah, so I'm going to talk about a tool called HPC Container Maker, which hopefully I will convince you that it does make containers easier. So I'm going to start out with just some introduction on why you would want to use containers, what containers are, and then I'll talk about HPC Container Maker and how it helps the process of making container images. So from systems like Blue Waters and Summit all the way down to your research computing system, one of the key metrics is your time to solution or productivity. So that means not only the time that it takes to actually run your simulation, but the time to build your workload, set up your data sets, all of those tasks that go into running a high performance computing simulation. And I like this metric because it really highlights there's a lot of tasks that people are doing depending on their roles that are not their key things that they want to do. So if you're a data scientist or an HPC researcher, you really want to do the science and the research. You want to spend your time analyzing the results that come out of the simulation, designing new experiments, and so on. You don't want to spend your time figuring out how to build an application for a software stack that's on a particular system, or rebuilding that software stack when the HPC system software changes over time. You submitted a paper, you generated some results, your reviews come back, 6 months, a year later, you now have to rerun some simulations, but your code doesn't work anymore because the operating system on your shared system changed. If you're a developer, again, you want to focus on new algorithms and code and things like that, not on supporting users running on some system environment that you've never seen before. Or if you're a sysadmin, you want to focus on uptime and adding new capabilities like optimizing your parallel storage system, not adding yet another math library that some user has requested. So all of these challenges to be a little more precise and articulate about them, really boil down to sort of these 5 categories. In that, running HPC software or AI software, for that matter, takes a lot of expertise. You need to be an expert on how to run those stacks, how to build and install those stacks. In particular, AI and deep learning software is evolving so quickly that as soon as you sort of figure out this is how I should build TensorFlow to perform in an optimal manner, it's already out of date. And you have to start over and do it again. Or you figure out how to do it, but you don't have the expertise to apply all the optimizations. So while your version of your molecular dynamics software runs, you left a lot of performance on the table because you didn't specify the right build flags or pull in the right libraries or things like that. And all of those things limit your productivity. You're spending time fiddling with these details and not doing your simulation, advancing your science. And from an IT perspective, trying to keep up with all of these changes and keep your user base in sync with the software environment can be a challenge. So I assert that containers are a solution to this problem. So what are containers? I've seen containers compared to virtual machines or static binaries, and there's some truth to sort of both of those comparisons. Containers are like virtual machines in that you encompass your entire software environment, your libraries, your shell, environment variables, all that in a nice single package that you can easily redistribute. They're not as heavyweight as virtual machines. Containers use the same kernel as your host operating system, so a container can spin up in a second or less than a second, where a virtual machine needs to boot an entire operating system. And so much heavier weight construct. So they're a little bit like static binaries in that sort of everything you need to run that particular binary is bundled up statically with it, but they're more expansive. Containers include not only the libraries, which a static binary would include, but as I said, the shell scripts and environment variables and everything else necessary. So by having everything packaged up, you're embedding that expertise into an easy to distribute package. That's something portable. So you can run a container that's based on a different operating system than the one on the host, but that's no problem. That's a problem that containers solve very, very easily. So as some of my colleagues like to say, the nice thing with containers is basically you can grip it and rip it. You just pull a container from a repository and start running. There's no time to bootstrap the software environment or anything like that. So this lets you get higher productivity. You're not as dependent on your IT staff anymore, so you don't need to ask them to install some version of a library. It's just part of your container, and you're now largely independent of the host software environment. So that's sort of the story of why you would want to use containers. It simplifies deployments. They're portable, reproducible environments. That problem where you submitted a paper and 6 months later you have to rerun some simulations, and the host operating system has changed in the meantime. That's fine. If you still have the container will still run on that host environment. And so you can get containers from places like Docker Hub or Singularity's library or other places. And those are great, very good. NVIDIA has its own container repository called NGC, and the focus of NGC is to have a set of curated containers. So if you go to Docker Hub, there's some very good containers on Docker Hub, there's some not so good containers on Docker Hub, and sometimes it's hard to tell the difference. With NGC, you're always getting containers that are optimized for performance, so we're continually updating those containers to make sure that they give the latest and best performance. We've also engineered them so their performance is scalable. They're designed to run on multi-node clusters with multiple GPUs. And for HPC containers, we validate them with both Docker and Singularity. We know that Singularity is deployed on many shared HPC systems for various reasons. And so we want to make sure that there's a nice, smooth runtime environment. We're using Singularity with the NGC containers. And they're designed to run anywhere on a system that has a Pascal or a later GPU, whether that's in the cloud, on your workstation, or on a shared HPC system. So this next slide is one of my favorites, and it really sort of hammers home one of the benefits of using containers. So not only are containers portable and reproducible, but because everything is bundled up, it's very easy to move from version to version. You're just pulling a different container, but your workflow is the same. So what's shown here is for different versions of the containers generated over roughly a year period, running on exactly the same hardware, the performance improvements. So the three figures on the left show some various deep learning frameworks, PyTorch, TensorFlow, and some DL benchmarks, Resonant, things like that. I want to focus on the one on the right because this is an HPC audience. So this is showing a basket of popular HPC applications, GROMACS, LAMPS, things I think everybody has probably heard of, and showing the speed up of running the NGC container compared to a non-GPU host system. So over the course of about a year, it went from a 10x speed up to a 16x speed up, so about a 50% performance improvement on the same hardware, no changes to the hardware, just do improvements in the libraries that are in the container, in terms of math libraries, communication libraries. In many cases, the codes were improved, and that's incorporated in the container. So in GROMACS, for example, in the March 2018 code, only the non-bonded forces were computed on the GPU using CUDA. Whereas in the March 2019 code, more routines have been ported, had been accelerated. Now some of the bonded interactions were also happening on the GPU. So you get speed ups from all sorts of sources, but they're very easy to take advantage of because you just download and use the latest container and everything's ready to go. So on NGC, we have over 50 containers now, and that's growing over time. So we have all the popular deep learning frameworks, TensorFlow, PyTorch, and more. If you're doing machine learning, there's the Rapids framework. So if you're doing random forest or XGBoost or K-means algorithms, that's a great place to go get accelerated machine learning container. And then we have a bunch of HPC containers as well. So NAMD and GROMACS, and just to cite a couple here, and many more. So NGC is a great place to go get pre-built, optimized containers, and you can, again, just grip it and rip it and be running in a matter of minutes with highly optimized workloads. So that's great, but what if your container image is not available from NGC? What if you're running an application that we don't have, or your research is adding new algorithms to a code like NAMD or games or something like that. And so while we have a version of those codes on NGC, it doesn't have your optimizations, it doesn't have your changes in them. So you need to build your own container image at that point. So if you need to build a container image from scratch, this is the workflow that I recommend. So first specify the content of the container image with the tool HPC Container Maker, which is what I'll be talking about today. Build those container images with Docker. Convert those Docker images to Singularity, and then use those Singularity images to run that on your HPC system. And I'll walk through why this is the workflow I recommend, but just briefly, the advantage of HPC Container Maker is it lets you operate at a much higher level when you specify the content of a container image. You can say something like, I want this compiler, this MPI, these libraries, in pretty much just a one-liner, very similar to what you would do in loading an environment module on a typical HPC system. Build the images with Docker. Docker images have some advantages over other container formats, in that they're layered, and you can use build caches and things like that. So you can really speed up building your container images by building them with Docker. Pretty much every HPC-focused container runtime, whether it's Singularity or Charlie Cloud or Shifter, works very well with Docker images. They're all designed to interoperate with Docker images. And so it's basically a trivial process to take that Docker image that you've created and convert it to a Singularity image. And then you can copy that Singularity image to your shared system and run it on your HPC system. And I'll go through this in more detail as we go. So before we get to HPC Container Maker, I just want to cover a few basic topics on building container images with Singularity and Docker. So let me first talk about just building container images with Singularity. If you want to skip the whole flow that I just outlined and said, I'm just going to build a Singularity image. What does that look like? Let me show you. With Singularity, you create a Singularity definition file. This is just a plain text file that specifies the instructions that should be executed when creating your container image. So there's an example below here, which is a complete Hello World example. So if you were to build a Singularity image with this, you would get a Hello World container. And if you've ever built like an RPM or work with an RPM spec file, the syntax should look pretty similar to you. You have these blocks offset with %files, %post, and so on. So what this is saying here is, let's start from an Ubuntu 16.04 container that comes from Docker Hub. So the bootstrap Docker says, go to Docker Hub and get the container, and then I specify which container I want, which in this case is an official Ubuntu 16.04 image. Then in the files block, I'm telling it to copy a source file from the host, sources hello.c, to a specific location inside the container images, var temp hello.c. And then in the post section, I'm performing a series of steps to actually build and compile that Hello World program. Now, this base Ubuntu image does not include a development environment in order to keep the image size small. So the first thing I have to do is install GCC. So this is Ubuntu, so I have to do apt-get install and get GCC and some other build tools. And then I can build my Hello World program, just like you would expect, just GCC. And so I can execute this with Singularity and build a container image. So a note: to build a container image with Singularity, you need root privileges. So sudo Singularity build. I specify the name of my image file that I want, hello world.sif, and my Singularity definition file, which is what I showed on the previous slide. So I do that. It builds the image file, and then I can do Singularity run hello world and specify the program I want to execute inside that container image, which is just called hello. So note that to run the container image, I don't need to be root. That's one of the reasons why Singularity is a popular container framework for running on shared systems. So I get the expected output, hello world. Okay, everything is great. Singularity is nice in that this container image is just a single simple file, hello world.sif. I can easily transfer it to other systems. If I want to delete the image, it's just an RM. Control permissions, it's a schmod. You work with it the same way you would a normal file. Now, one thing I want to point out is this hello world image that we just created is 93 megabytes. And I want to contrast that to the base Ubuntu image, which is only 36 megabytes. So I've almost tripled the size of this image to distribute a hello world binary, which is only 10K. So that seems kind of excessive. So why is this image so big? So as you probably realize, it's because we had to install our development environment in order to build the Hello World program. GCC and other build tools are what account for the 60 megabyte or so increase in the container image size. So for Hello World, that's not a big deal. 93 megabytes is not that big. For a real-world HPC application, this can grow into gigabytes. And you start throwing a couple of these large images around, and suddenly you're filling up disks, which is not good. So for Singularity, the approach you would take would be to add the text in green here to your definition file. So after I build the Hello World program, put in some steps to basically remove the development environment that we just installed. And you can do this. It works okay for Hello World. If we do this, the resulting image that we get will only be 36 megabytes, basically the same size as the base Ubuntu image we started with, plus the 10K for Hello World binary. But this can get kind of tedious, especially if you have a lot of HPC components. And Hello World is nice and simple in that it really just depends on libc. If I start getting dependencies on an OpenMP runtime, MPI runtimes, math libraries, trying to remove components while still keeping the ones that I need as runtime dependencies for my workload can be very tricky and cumbersome. So this is why, or one of the reasons why I do not recommend just building Singularity images directly. So let's look at building images with Docker. How does that differ? So As we just saw, with Docker, it's called a Docker file as opposed to a singularity definition file, but the concept is very similar. It's just a text file that specifies the steps needed to create your container image. So there's an example here. This isn't Hello World. We'll work up to Hello World, where we start from a same Ubuntu 16.04 image from Docker Hub. Syntax is a little different, but the idea is the same. And I'm going to do 2 steps here. I'm going to take the output of date and uname-r and just add it to a file inside the container image. So when I build that, I need, again, root access. So I have to do sudo docker build. I specify the name of the image that I want. In this case, I'm just calling it layer example in my Docker file. With Docker, you need to be root to run your image, which is one of the reasons why Docker is not widely deployed on shared systems. So I can do sudo docker run and run my image and cat this file, and I get the output that I expect, or the output that I generated when I did this example last week while preparing for today's webinar. Now, unlike Singularity, this Docker image, you don't get a file that comes out. It's this amorphous thing. So we have these tools to interact with it. One of them is Docker history. And so if you run Docker history on this image, you'll see there's some layers here, starting from the bottom up, that start from the base Ubuntu image that are all from 11 months ago, and then the 2 layers that I just added, the date command and the uname command, which were in the Docker file. And the thing I want to point out is the size of those layers. So the first layer was 29 bytes. If you count out the date, it's 29 characters. So that's where the 29 bytes come from. But the uname-r, the size is 57 bytes, as opposed to, I think it's 27 or 28 bytes of the actual link. So why is that larger? Why didn't it just capture the incremental change? And that's because of the layering structure that's the basis of Docker images. Doesn't capture the diff of a file, it captures an entire file. So a pathological example would be this is I have some very large file and I change 1 byte in it. I've now essentially doubled the size of that file in the container image because it's going to store the original and then a layer on top of it. You can sort of think about it as like a painting. If I paint something, I have the image that I painted and then I can paint over it, but that doesn't erase what was under it. It's still there. So I'm building the image up from the bottom, layering 1 layer on top of another on top of another, and then when I'm done, I have some final image, which is what you see when you run the container. So this layering has advantages and disadvantages. So let me compare and contrast the container image formats. Singularity images are flat, so it's only recording the final change. If in my singularity definition file, I had that large file and I changed 1 byte in it, I would only have that final state stored in my image. It's a single file, so you can easily transfer it to other systems. Some of the new versions of Singularity support signing and encryption, which are really useful features if you want to know the provenance of your containers or restrict usage. Those are really cool new features. Docker images, on the other hand, are layered, as I just showed you. So one advantage of that is when you build container images, if a layer already exists in the layer cache, it doesn't have to rebuild it. So if I'm building some complex HPC application that takes several hours to build the application, all its dependencies, and in the very end of that, some remote repository that I'm pulling code from decided to flake out and be down, I'm not completely out of time. It can essentially restart from that last step that failed when I try to rebuild the image. That differs from Singularity, which always rebuilds the entire image from scratch because it doesn't have this notion of layers. On the other hand, Docker images are opaque. There's not a single file. The Docker image is actually stored in varlib docker, and there are multiple files. So there's some metadata files. There's a bunch of tar files that are these individual layers that get untarred on top of each other to form the final image. Docker images do conform to the OCI standard. So while I'm referring to them as Docker images, and many people refer to them as Docker images, they're technically speaking OCI images. And that's one of the reasons why they're pretty much supported in any container runtime, whether it's Shifter or Charlie Cloud or Singularity. They're all working off of this OCI standard, and they all interoperate with it very well. So as I say here, Singularity can easily import the Docker images. So you can build with Docker and then convert to Singularity. So let's look at Hello World again from a Docker perspective. So I can start from the Ubuntu image. I need to install my development environment again. And notice here in the development environment, I'm using this and syntax to string commands together. And you'll see that in a lot of Docker files. Have you ever looked at Docker files on the web, for instance? And that's to address this layering concept. So I want all of those steps to occur in a single layer. If I had executed them as separate run commands, they would each be a separate layer. And if they were touching the same files, I'd be duplicating those files inside my container image. Copy the source code in and then run GCC to build it. And I can do that, build the Docker image, do sudo docker run, and hello world. We see the same problem here in terms of we've now created an image that has the development environment in it. So while the sizes are different, in the case of Singularity, there's some compression that happens in the images that don't apply to Docker images. So the sizes are bigger for Docker, but you'll notice it's the same, about 3x increase in the image size. And that's the comparison we should be looking at here. So we still have this same issue. So with Docker, since it's a layered approach, one of the things that we can do is use multi-stage builds. And so we can basically concatenate two Docker files together in a single Docker file. And so the first part up here, the build stage, is identical to what I showed you before, except I added the text in green as build. I'm naming this stage. I'm calling it build. And then I can basically append this second Docker file at the end that starting a new image, still based on the Ubuntu. And I'm just going to copy my Hello World program out of the build stage into the runtime stage. So when I build this Docker file, it's still going to execute both stages using the cache if possible. But the final image will just be the base Ubuntu image plus my Hello World program, nothing more. So if you don't want to distribute your source code, if you don't want to distribute your development environment, multi-stage builds are a great technique for doing that. And this is something that's supported natively in the HPC Container Maker tool. So let's actually talk about some HPC stuff. So if you land on most HPC systems, you're probably using environment modules. So if you land on, say, a CentOS 7 system with some version of Mellanox OFED, you're going to load some development environment, and then you're going to build your application, some MD code or chemistry code or whatever. So what's the equivalent Docker file to do that? So you might say, okay, well, I know I want to use CUDA, and I know I want to use CentOS, so I'm going to go use one of the base CUDA images that NVIDIA provides. NVIDIA provides base images for CentOS and Ubuntu, for multiple versions of CUDA, and they're a great place to start if you're building CUDA applications for containers. But then what do you do beyond that? So if you're like me, or, you go off and search the web, you look at Stack Overflow, okay, how do I put OpenMPI in a container? And so these are 6 examples that I just sort of arbitrarily picked from Docker files that I found on the web. And so all of these will get you OpenMPI in a container. Some are better than others. So the first example up there, A, is just using OpenMPI from the Linux distribution. So whatever's distributed with Ubuntu, we're just going to install it, put it in the container. That's real easy, but what do you know about that OpenMPI build? Was it built with InfiniBand support? What version is it? You have no idea. The second one here, B, builds it from source. It's not building the version that we wanted. On the previous slide, we wanted version 1.10. Here we're getting version 3, but maybe we can hack this up and get the version that we want to build. But B is pretty good. It's all executing in a single layer, and so on. C is another example. Here it's using the PGI compiler. It's using 2 layers, and so on. So I'm not going to go through all of these other than just to note that there are pros and cons for all of them, and it's not really clear which one you should pick if you were trying to build a accelerated MPI application inside a container. And that's where HPC Container Maker comes in. So this is the problem that the HPC Container Maker is trying to solve. So it's a tool for creating Docker files or singularity definition files from a higher level Python source. So you write recipes in Python, and then they're converted into Docker files or singularity definition files using HPCM. And it's based on this idea of building blocks. So there are building blocks for these HPC components. You can say something simple like, I want OpenMPI, and it will go generate a Docker file snippet or singularity snippet to install that in a container. This is open source. It's up on GitHub. It's very easy to install. You can just do pip install HPCM and have this on your system. So let me show you what something like this looks like. So in your recipe, you would say something like stage 0 plus equals OpenMPI. Stage 0 is just the first stage in a multi-stage recipe, so we're adding OpenMPI to this first stage. And when you process that through HPCM, it'll spit out this Docker file blob that I show down here. So this is the default, or the defaults as of the time I generated this slide. So you can see it goes and gets OpenMPI version 3.1.2, installs some dependencies from the host Linux distribution, and then builds OpenMPI from source with some flags. Then installs it, and it configures the environment inside the container. So I assert this is much easier to do and more maintainable than actually typing out the blob below. And let me give you an example. So in earlier versions of HPCM, it didn't install the NUMA CTL devel package as a dependency. OpenMPI builds fine, no problems, but it would silently turn off process pinning because it didn't have the library calls to figure out the NUMA domains of the CPU. And so while it was functionally running, you weren't getting the performance you would expect because it wasn't pinning the processes to the various cores. So once we discovered that, we fixed that in HPCM, and we added the NUMA CTL devel package. And if you had written your own Docker file, you would have had to go back and manually know to add that and then add it. Whereas if you had generated an HPCM recipe, all it would have taken is reprocessing your recipe with the HPCM tool, and it would have spit out the new optimized Docker file for you automatically. So this is the defaults. You're probably thinking, well, I need it a little bit differently. In the example that I motivated this with, I was looking at version 1.10 of OpenMPI, not 3.1.2. So all of these building blocks have lots of configuration options. So you can interact with them at a higher level. So here I'm showing actually just a subset. There's more than what I'm showing here. But you can do things like, change the configure options, enable or disable things like CUDA or InfiniBand or UCX just with simple flags, change where it's installed with a prefix, change the OS packages that get installed as dependencies, and change the version. So if you wanted to use version 1.10.7, you could do something like the example below and just say version equals 1.10.7, and that's what HPCM would generate for you. You can also do things like set the tool chain. So if you wanted to build with an alternative compiler like PGI or CLang or something like that, there's a very easy way to do that as well. So it's this higher level interface to working with container specification files. So let's go back to the example that I started out with. So, on the bare metal, we load some environment modules, and we can build our application. We have our environment set up. HPCM is designed to be very analogous to that. So we have, a stage where we add a base image. We want to start from a CUDA base image that's based on CentOS 7. We want to install the Mellanox OFED stack user space libraries from version 3.4-1, install the GNU compilers, and install OpenMPI. So now we have an environment inside the container that's basically analogous to what you would have on bare metal after executing that. So now you would put in your Docker file or your Singularity file, the steps to build your application. And the result of that is now you have a portable application container that you can run on basically any system, as opposed to an application binary that will only run on that particular bare metal system. You can't really copy a binary you build on Blue Waters and then go run it on Summit. Of course, that's a trivial example because they're different CPU architectures. But if there was another x86 system, odds are that binary wouldn't run because all the software packages are installed in different places on that other system. And while the versions here are kind of dated, this is actually one of the advantages of containers. So there are many systems that are sort of stuck on old system stacks because there's one or two mission critical applications that just won't run on the latest OSs. And so what you can do here is you can generate a container that has the old, say, CentOS 6 or old version of Ubuntu or whatever for those containers, and then you can update your host software independently from that. You're no longer stuck on those older versions. The converse of that is also true. If you're so bleeding edge that your sysadmin staff doesn't want to install the software you're requesting because it's unstable, untested, whatever, you can break that dependency. You can install the software that you want in the container independent of your IT staff. So by using containers, you get a lot of flexibility, both to be cutting edge and very retro. So let me show you the list of the building blocks included in HPCM. So as you expect, pretty much all of the common HPC building blocks. So you get your choice of compilers. One of the latest additions to HPCM was the ARM compilers. So if you're building ARM container images, you can now use those compilers from ARM. A suite of HPC libraries, miscellaneous tools. Another recent addition was Julia. Julia is making great strides in more productive computing. And so now you can build Julia containers more easily. OFED and other communication libraries, your choice of MPI stack, and other things. So, pretty much we have you covered. If we don't, this is all up on GitHub. Please submit an issue. Let us know if there's some package you need that's not here. Or even better, submit a pull request, and we can add it to HPCM. So let's take a look at Hello World as specified in HPCM. So this isn't the best example because it's so simple. It doesn't really show off the power of HPCM, but you can get a sense of what a more realistic recipe would look like. So again, you start from a base image. Here again, it's Ubuntu 16.04. I want to install the GNU compilers. I need my development environment. I'm telling it to not install the Fortran compiler, so I can save some space. I could install the Fortran compiler. It doesn't really affect this example. Copy the sources into the container, and then execute the GCC command. And then here I'm showing the multi-stage build. So I can do stage 1 very easily in HPCM. You see the stage 1 plus equals stage 0.runtime. So this will pull all the runtime components from what I chose to install in the first stage. So this will pull the GNU runtimes and install those in the container. So in this case, Hello World only depends on libc, but this would pull in the OpenMP runtime, the Fortran math libraries, and things like that. And then I can copy the Hello World program. So this is the HPCM recipe, and by doing that, I then have the single source Python recipe, although it doesn't look too much like Python, and with that generate the Docker file or singularity definition file from that. So I have a single source now that I can use to generate a multitude of different configurations, and then use my normal workflow to build the Docker container or singularity container from this point. Of course, I can always go in and hand tweak these files as well if there's something that just can't be captured or needs to be done. So let's take a slightly more complex example. So this is using the MPI bandwidth proxy application from Lawrence Livermore. So here I need a more sophisticated stack. So here I'm going to start from a CentOS base image. I need a compiler, I need a Mellanox OFED stack, and I need an OpenMPI. So these are all just one-liners. I'm putting those in my container image, copying in my source code, and then executing the MPI compiler wrappers to build the MPI bandwidth application. So, pretty straightforward stuff. And then in the second part of the file where I'm doing the runtime stage, I do stage 1 plus equals another base image. I get the runtime, so this will pull in the runtime automatically of the GNU compiler, the Mellanox stack, and OpenMPI. So in that one-liner, I'm automatically copying those runtime libraries for all the components that I picked in the stage 0. And then I'm copying the MPI bandwidth binary itself. So this is like, if you don't count comments, it's like a 9-line recipe. And from this 9-line recipe, I can generate this. Now, this is an eye chart. I'm not expecting you to read it. In fact, I'm putting it up here with the explicit point of not expecting you to read it. So from that 9-line recipe, I'm turning it into 40 or 50 or 60 lines. I don't remember the exact count of corresponding Docker file or singularity definition file. So I assert that you would rather maintain and develop this simple recipe than one of these much longer, more complex Docker files or singularity definition files. And HPC will automatically use the best practices that we talked about in terms of making things happen in a single layer, making sure that you clean temporary files up in the same layer where they're started from so you don't bloat your image sizes. So this concept is basically from an HPCM recipe, you have one recipe and multiple targets. So both in terms of container format, so you can generate Docker files, singularity definition files. One thing I haven't talked about is you can also just output a bash script. So if you did want to execute some of this on bare metal, you can get the bash script equivalent of these steps. And you also have a choice of Linux distribution. So all these building blocks are aware of the Linux distribution that was picked. So if you pick CentOS, it will use Yum to install its dependencies. If you use an Ubuntu or a Debian-based image, it will use apt-get to install those dependencies. And a new dimension that was just recently added is the processor architecture. So we've always just done x86 container images, but now HPCM can also be used to generate Power or ARM container images, all from a single recipe. So let me show you a very simple example of that. So this is charm, which is probably of extra relevance here at Illinois. But you can see the simple 3-line recipe in the middle here. So I'm picking a base image. Here you can see the power of Python. So HPCM has a user argument capabilities, a lot like the Docker build arg. So by default, it'll use a CentOS 7 base image, but if I specify a command line option, I can change that base image. Then I'm installing the GNU compiler and then the charm runtime, building the charm runtime from that. So I'll show 4 examples from this same base recipe. So if I just do HPCM recipe charm, I get the thing on the lower right, which will use CentOS image and Yum to install everything, and we'll install or build an x86 version of charm. So this is sort of a trivial example in that really the only change is you're telling charm to build the multi-core Linux x86 package in that case. From that same recipe in the upper left, I can tell it, okay, I want a singularity image. It's still CentOS, so it's still using Yum, still building x86 target. I can tell it that I want to build an Ubuntu version of this with the example in the upper right. So I just do the -- user arg image equals Ubuntu. And now it's going to use apt-get to install its dependencies, but still build an x86 version of charm. Or in the lower left, what we just added was support for alternative architectures. So if I use the ARM64 v8 CentOS 7 architecture, or base image, it will use Yum to install the packages, but it changes the charm build target to multi-core ARM8. So it picks all these things up for you automatically. So you can have a single source package, or a single recipe, and basically build it for all these different permutations. So hopefully in many of your minds, that's thinking, well, this might be really useful for CI/CD type applications. And people have been using containers for that purpose for a while now. Here's a paper from PERC last year, where they basically, you took workload stored in Git, and whenever you checked in a change, it would fire off a Jenkins set of tasks and build a bunch of Docker containers and then run the test suite unit tests inside those containers. And if it passed, it would promote the change. If it failed, it would kick back images kick back messages to GitHub. And while they didn't use HPCM for this, they just had some handcrafted Docker files. You could inject HPCM, as I showed, in the process at that point and have a single HPCM recipe that could generate all these different permutations. Now, let me sort of walk through how you would do that. So, if you put on your hat and say, I'm a developer of HPC software, and I need to validate that code on a bunch of different configurations that my users have. Maybe they're using different compilers to build the code. Say they're using GNU, LLVM, and PGI. They're using different MPI libraries, and they're running on different Linux distributions. So just for those 3 versions of those 3 things, you're already looking at 27 different combinations. And we're not even looking at different versions. You should probably test with OpenMPI, 1, 2, 3, and 4, and different versions of CLang and things like that. And so you can use HPCM to generate containers that cover all these different combinations from a single recipe. So let's do that for MPI bandwidth, just as an example proxy. So for each for each of these configurations, we're going to just, does it build successfully? Does it pass the tests that we've defined? And there's a Python script, which I'll show you on the next slide, which takes a bunch of command line options to generate these different permutations. So I can just run the command and specify whatever combination I care to generate. And it'll spit out the corresponding container spec file. So here's the complete script for that. Here I'm showing you another capability of HPCM. So the previous examples showed a recipe, quote unquote, which is something you process through the HPCM command line tool. This is a standalone script, Python script. So you could just do import HPCM, and now you have a standalone Python script. And so all the stuff on the left here is basically just processing command line arguments, nothing fancy. And once you've done that, you just can call the HPCM components that you want to pull in. So depending on your base image and your compiler and so on. So one thing I'll note is for the compiler, you'll see that it's a compiler equals, and I'm picking one of the compilers. And then for MPI, I'm calling toolchain equals compiler.toolchain. So that'll tell HPCM to use GCC if you're using the GNU compilers, or CLang if you're using LLVM, and so on. And then in lieu of a test suite for MPI bandwidth, I'm just going to run MPI bandwidth, so you can see that it's just doing MPI run and verifying that runs successfully, and then printing out the corresponding Docker file. So you could run these, integrate this into your CI/CD infrastructure, and people are doing this. So there's a library called CUDA, which is for quantum chromodynamics. And so their CI infrastructure is GitHub with Jenkins and Singular and HPCM. So they're testing multiple combinations of their OS, compilers, CUDA toolkit versions, CMake versions, and all of that. And this is an integral part of their development process. So you can see that there's a nice quote here from one of their contributors saying that this has really simplified their life. They don't have to worry about trying to set up these different environments manually. They can just do it all through HPCM. So let me wrap up. So to help you get started with HPCM, there are a number of sample recipes included. So there are what we call base recipes, which are just sort of a common development infrastructure with a compiler, an MPI library, and common frameworks like HDF5 and FFTW and so on that are a good starting point. Of course, you can and should customize from that. In addition to that, there are some full application recipes for GROMACS and Milk. So you can go build those, show you how to build a complete application using HPCM. There are also recipes for EasyBuild and SPAC. So EasyBuild and SPAC are great tools for trying to solve some of these similar problems for bare metal, not using containers, but you can also call them from inside a container. Now, I do want to point out that EasyBuild and SPAC are not really container aware. So, for example, you can build GROMACS using either of those tools in a container, but the container image you get is not going to be as optimized as the one you get from HPCM, or you can go download from NGC. So, for example, for GROMACS, with EasyBuild, you're going to get a container that's like 4.5 gigabytes. SPAC for the same sort of configuration and setup is 2-something gigabytes. With HPCM, it's 500 megabytes. Same code, same functionality. The difference is HPCM was built from the ground up to be container aware. And so it can take advantage of things like multi-stage builds, good layering, and so on to really minimize those container image sizes. So let's revisit this process of building container images from scratch. So the workflow I recommend is to specify the content of your container image using HPC Container Maker. You can take advantage of the building blocks and everything that's integrated in them in terms of best practices for containers as well as the HPC components themselves. Use that to generate a Docker file, and then use Docker to build the container image, which is shown in the second step. You can then easily convert those Docker images to Singularity images using Singularity. Very straightforward. You can do this on your local workstation, where you presumably have sudo access. And then once you've created the Singularity image file, the CIF file, you can just SCP or some other tool to transfer that to your HPC system. And you can take advantage of using Singularity on that system to run your container and have a reproducible, portable software environment. So in summary, HPCM, hopefully I've convinced you now, or hopefully I've convinced Maxim, that the tool simplifies the process of creating container specification files by using the best practices and building blocks, gives you the flexibility and power of Python. So I just sort of barely scratched the surface of that, but you can do all sorts of cool things like validate your input, have all these flags that you can set, and so on. And you can use that to generate multiple source files from that single source. And you can just do pip install HPCM. So as a call to action to you guys listening, if you're a data scientist or a researcher, take a look at the NGC containers. Hopefully you can find something that suits your needs there. If you can, great. Download it, run it. You're going to be in great shape for running any sort of accelerated workload by just using the NGC containers. If you're a developer, please start distributing your software as container images. It will make things much easier, make your job easier. Now you have a defined software environment to support, as opposed to sort of the Wild West of how people may happen to build things on whatever system they happen to be on. So these slides hopefully help you. There's a blog. There's other material that you can get on the HPC Container Maker GitHub page. If you're a sysadmin, one of the things you can do to help your users is there's a tool called NGC Container Replicator. So that will automatically create a local replica of all the NGC containers. So rather than having each one of your users download their own TensorFlow container from NGC, this will do it automatically for you, put them in a shared directory, and then you can point your users to that location. And as we publish new containers monthly, it will automatically download them and make them available to your users. So with that, I'll stop. And if there are any questions, I'd be happy to answer them.
All right. Thank you very much, Scott. It was a very interesting presentation, and I think HPCCM is the tool that has been missing in the tool set of developers, and I think this is a really interesting and useful tool. So let me ask a few questions that I actually wrote down myself while you were presenting. So first, you mentioned an issue with NUMA CTL. So my question is, how do you currently vet HPCCM building blocks?
So all of the container images that we post on NGC, or at least all of the HPC container images, are built using HPCM, so HPCM recipes. And for all those images, we put them through a very extensive validation process to make sure that they get the same performance we get on bare metal. They work with Docker and Singularity. And so through that process, we identify issues like that. And then once we identify them, we go in and start debugging them and figure out that, oh, it was this missing package, we weren't setting the affinity properly.
All right, thank you. So my second question is related to some options, configure actually options that I noticed. So I saw some hard-coded options. I don't know, maybe it was just an example, but this led me to the following question. How can I make sure that configure options that HPCCM uses are optimal for the HPC platform that I'm intending to use it on?
Yeah, that's a great question, and that's something that there's still a little bit of hand tuning that has to happen there. So the design philosophy of HPCM is largely to produce portable container images, and so we don't try to over-optimize. For example, it doesn't assume you're running on a CPU with AVX instructions, or you are at Volta GPUs, and so you can use SM70 capabilities and things like that. That said, there are many software stacks that sort of automatically add a mtune equals native type compiler flag, and that can limit the portability of your containers. So it's a bit of a trade-off on whether you want to highly optimize for your specific host environment or do something more general. What we do in the NGC containers actually is we create, or they embed several binaries. So we have, say a GROMACS binary optimized for Pascal GPUs and a separate binary optimized for Volta. And at runtime, we detect the host platform and set up the environment to choose the right one automatically. Another option that you can do is build fat binaries. So specify multiple instruction sets, basically, and embed them in a single binary. So that's something that the person building the container recipe and building the container needs to specifically watch out for. But that is an area that if there's any great ideas on how to make that a little bit smarter, I'd love to hear them.
All right, thank you. Yeah, it looks like there is a tug of war between portability and performance in this case. Yeah. So, and my last question is, would you like to highlight some features or issues that you are currently working on?
Yeah, so what the latest big change to HPCM was adding support for other CPU architectures. So we added Power and ARM in addition to x86. And it's really cool, in my opinion, in that from a single source recipe, you can basically generate all these different combinations. And HPCM is smart enough, based on your image name, to figure out not only the distribution, but also the architecture, and can tailor its behavior accordingly. And so adding new things like the ARM compiler building block, to let people do that, or to use ARM containers better, I think is an exciting area, and I'd love to see more activity there.
All right, thank you very much. Let me check Slack and YouTube. So we don't have questions at this moment. So let's switch to the final slide. First of all, I would like to thank Scott once again for the interesting webinar today. I hope our viewers will give HPC Container Maker a try and maybe start using it on a regular basis. Our next webinar is scheduled for next week and is titled E4S, Extreme Scale Scientific Software Stack, and will be presented by Samir Shandeh from the University of Oregon. This webinar will feature hands-on activities, so if you would like to participate in these hands-on exercises, please send us an email at bw-eot@ncsa.edu. illinois.edu. And by the way, in that webinar, Samir will be using SPAC inside of a container to build MPI. So it looks like it's very related to our current webinar. And since we're on the topic of future webinars, the webinar after the next week's webinar is on SPAC. So we are in business here. So once again, thank you all for joining us today, and we hope to see you in the next webinar.